Guys, welcome to another ARC seminar. And today our speaker is Prof. Martin Bucher from the University of Paris. And today's talk is going to be about detecting global 21 centimeter signal as a part of this REACH collaboration. And he's a well-known figure in theoretical and observational cosmology. And most of us already know his work. So yeah, Prof. Martin, please go ahead. The stage is yours.
Okay. Well, this talk is going to be maybe a little different from, the advertised title, because I'm going to relate observations of the global 21 centimeter signal to, other observations of the CMB spectrum, and I sort of want to explain why this is a hard measurement. And, this goes a little outside my area of expertise because I, recently joined the REACH collaboration, and, there are certain parts of the effort that I know, I think, really well, but then there are also a lot of areas that I don't know so well. And, I also know that I don't know the present status, but, your institution has been working on the PRISM experiment on Marion Island. So you probably heard sort of some similar talks, but I hope that some of this is a bit different. And, I'll also talk a bit about the underlying science. Let's see, why isn't this? Oh, okay. So the first part, what is the 21 centimeter global signal? Why is it interesting? What has been claimed? So, this is this EDGES result that I think a lot of people find surprising and don't completely believe. And then I'm going to talk about some techniques for measuring the CMB. So this is going to be, some of the stuff that's not in your typical CMB experiment talk, that sort of explains in a rather schematic way some of the challenges and things that you have to get around. Then I'll talk about making absolute measurements of the spectral distortion in the extreme Rayleigh Jeans tail. So it's a rather, mouthful title, but you'll see what I mean about this. And I will end with some stuff about calibration, amplifiers, and noise. And noise is something we deal with in all sorts of measurement and engineering applications, but some of the requirements here are rather unique. So that this, it's not like you can just take standard electrical engineering stuff off the shelf and just use it in the standard way. Okay, so we you've probably seen this slide before, and this is rather old. So that this is the short wavelength, the blackbody spectrum of the CMB. So this is taken from FIRAS, which is from 1992, from the Kobe satellite. And this remains the best measurement because, nobody's been willing, to date at least, to pay for a better satellite. And this kind of measurement has to be made from space. And here you see the actually the observations in the theory curve, the error bars are so small that you can't really see the difference. So that, this is its short wavelength, something like 90 gigahertz or something like that. And then when we go to different frequencies, there are these, different foregrounds. So there's a sort of window around, 70 gigahertz where the CMB dominates the sky the most. And then when you get to lower frequencies, the synchrotron is roughly power law, and that eventually takes over. So for the frequencies that we're looking at, the CMB, and not just the isotropy, the monopole is kind of a sideshow. So we're going to go down in frequency by about a factor of 1,000. So what we're interested in is absorption or emission by the atomic hydrogen. So this is 1.4 gigahertz without being redshifted. And then when you go to larger redshift, the resonance, this hyperfine transition of atomic hydrogen shifts to lower frequencies. And when this spin system, so this is alignment or disalignment of the electron spin and the proton spin, so you can associate a spin temperature, and if that's higher than the CMB temperature, then there's emission and stuff added to the spectrum. And if it's colder, there's absorption. So that's sort of the physics. So we would be able to calculate a spectral distortion if we knew what was the fraction of the protons in the form of atomic hydrogen. The electrons are paired in molecular hydrogen, so there's no such line. And if it's ionized, and then the other ingredient is the spin temperature. So if you know those two functions at redshift, you can get a prediction for the spectral distortion. So here is the prediction, and let me say this is quite different from Hyrax, because this is the average signal, and Hyrax looks at differences in temperature in the sky. Because it's an interferometer and there's sort of no absolute calibration. So, Hyrax has its challenges, but here the challenges are quite different. And what you see, okay, so zero redshift would be 1,400 megahertz. So we're going up quite high in terms of redshift. And, 0 megahertz would be basically infinite redshift. But what happens is you get the atomic hydrogen first. The spin system is coupled to the radiation, then it decouples. And so we know that the kinetic temperature of matter since it's non-relativistic, it scales as 1/a squared, so it cools faster than the radiation. And when you have a lot of collisions between hydrogen atoms, or then there's an equilibration between the spin temperature and the kinetic temperature. So that's what gives us sort of downward dip. Then it sort of goes up again because the universe thins out and there are less and less collisions. And then something kind of paradoxical happens, that if you have ultraviolet radiation, so this is Lyman alpha, that sort of provides a collisionless coupling between the kinetic temperature and the spin temperature. So I'll show you how that works in the next slide. So that gives you this this sort of trough, and this goes down like 100 millikelvin. So you should sort of remember that when we talk about the edges claim, and then eventually having enough ionizing radiation heats stuff up, so the atomic hydrogen spin temperature is hotter than the CMB, so you get spectral distortion in the other direction. So you can see that this area here is, if you want to see a signal, this is the easiest place to look. And then I think the other thing is, the things I told you about at the beginning with the matter redshifting, the matter temperature shifting, redshifting faster than the radiation. Well, you wouldn't really want to put a lot of effort into testing that, because that's pretty much straightforward physics. But with this, cosmic dawn and reionization, we don't really know how that happened. So this is an important probe. So that this is also, I think the most interesting part of the spectrum to probe. It'll tell you something about the universe that we can't really otherwise tell. So how does this coupling work? So this is kind of weird because we have this, fraction of an electron volt splitting, and you would think that photons that are, I think 10.4 electron volts, there are very few of them, that they would have little effect. But you sort of see that the relative population, I won't go through all of this math, but there's sort of a temperature associated with the relative population within the resonance. So this is sort of how the number of photons goes down as you get the higher energy. And basically, the high energy photons dissociate and knock the electron up, and it goes back down into a random position. I didn't take into account the triplet, but this spin temperature gets equilibrated with this temperature, and then you have sort of a similar coupling with the kinetic temperature, because each atom is the position of the line is determined by the, width of the Doppler distribution. So what you see here is, well, you're sensitive to the total amount of ionizing radiation in this transition, which, has a rather small heat capacity. So it creates this coupling. Let's see. So this is the paper from Edges, and where they put this antenna in the desert in Australia, and it's sort of two pair of dipole antennas, and it very roughly looks in all directions and, gives you this average signal. And if you look at the raw signal, this is their analysis. The first thing you see is this power law from the synchrotron radiation. And you can see the brightness temperature, is from, 5,000 to 1,000 degrees Kelvin. So it's pretty hot. And then the belief is, and we know the physics of synchrotron emission, that this is smooth, so then you can subtract off or filter away this, and there are other residuals, and then they take this trough and they create a fitting function, and they claim something that is about twice as large as the amplitude expected. So let's see. This is from a paper with, various models, and as you can see, there's, quite a bit of uncertainty. And if we would know exactly which curve were the right curve, we would learn something about star formation, or the formation of the first stars and quasars. But you can see that minus 500 millikelvin cannot be accounted for by the present models. So there are a number of experiments and, reaches at the bottom here. And here is Prism on Marion Island. CNRS doesn't, they claim that their data is not consistent with Edges. And Reach is just starting to take data. There are not two antennas yet. There's just a single antenna. But I'm not really going to talk about the state of the experiment that much, because, things are getting debugged. There really aren't any interesting results yet. So I'm going to shift gear and talk a bit about measurements of the CMB and, some of the tricks. So the first thing is that, you do not measure the CMB temperature directly. So I just put a few examples of experiments. So this is from WMAP. And what they do is they have two telescopes that look at different parts of the sky. And then they split the signal coherently through two amplifier chains and switch back and forth, and then recombine it. And so this sort of switches from one side to the other side. So why do they do that? Well, at this frequency, the amplifiers have a gain that is not steady in time. So they can't really, with these gain fluctuations, get a consistent result. So what you do is you switch, since each beam goes through both these amplifier chains, and you switch and back and forth so quickly that the gain is constant, then you measure the difference, that the sort of square wave difference in the output, and that way you, with not very stable equipment, you can make a map from differences in the sky, and then it's sort of a question of map making. Now, if we go to bolometric technology, which is what Planck and a lot of ground-based experiments, or most ground-based experiments now use, you have detectors that are stable over a number of seconds, maybe 15 seconds or so. So they move in the sky, and you just filter out the low frequency part. So it's the differences that actually go into the map making. So this is the noise. It has white noise, and then a low frequency XX noise, which it's not exactly 1/f, but this gives you complete instability when you compare over long times. So let's see. Well, this integral diverges over a long time, so it's logarithmically divergent. So basically, the idea that everybody uses in CMB and isotropy is, you just measure differences at different points in the sky. So they never get the absolute temperature. They don't know what T0 is, and you can do a lot of science that way. You don't need to make an absolute measurement. Let's see, I'll speed up a bit, but you sort of want to, for the low L multipoles, you want to, which is particularly important for polarization, you want to sort of move over the sky so that you very rapidly go to the opposite side of the sky. So you have a lot of comparisons for the low L multipoles. Let's see. Yeah, so these are the map making equations, and it's pretty straightforward statistics, how to go from a map M from the data, if you know the character or the statistics of your noise factor. So you just do this, and this is the low pass filter. If you had this 1/f noise that you just completely get rid of all of the low L multipoles, and then you put them in. So this downweights differences where the, time difference between the measurement is large. Okay, second trick, and phi ras. So this is in a sense an absolute determination of the blackbody spectrum, but it really isn't, or at least not the way the experiment is done, because what you do, and this is the setup, there are these sort of wire beam splitters, and you have this mirror that changes the path length, and you make a perfect or nearly perfect blackbody, a blackbody that is artificial, that you think is better than what you think the CMB might be. And then you steer in a frequency dependent way the sky beam back and forth and the calibrator beam back and forth. And so they alternate between the left detector and the right detector. And you just record the difference in intensity with these two detectors. So Pixie is an experiment that's was proposed by Goddard Space Flight Center, Al Kogut, Dale Fixon, and others to do a better job than phi ras, but it hasn't been approved. And here is their more perfect blackbody. So this looks quite a bit like, if you go to some studio to test audio equipment, they have these sort of perfectly absorbing walls, and they have things like foam rubber to completely eliminate reflections. So the perfect absorber is also the perfect emitter. And if you can keep all of these little spikes, so here they're made out of epoxy with some sort of conductor, or something that's lossy that partially conducts to completely absorb everything in the frequency range of your Fourier transform spectrometer. And this is kept at a temperature like that of the sky, and you take data by recording the difference between your artificial black body and the real sky. So you can do that pretty well in that sort of, 50 to 150 gigahertz part of the spectrum where the CMB dominates. Okay, the reach experiment. So let's see, there's a Nature Astronomy article which summarizes the experiment and, how it's different from other experiments. So if you want to find out more, this is the place to go. So Eloy de Lira Acedo, who's at Cambridge, is the PI, and the co-PI is Dirk de Villiers, whom I think you know. So he's an engineering professor at Stellenbosch, specializing in antennas. And let's see, this is at the SKA site. So I think I don't need to explain to you what is, how this site is unique, because that's something most of you already know. I don't know if this is in Carnarvon, which is, when we go out to the reach site, this is where we stay. And this is in one of the bars in town, and I was very surprised to see a photo of Queen Victoria. So when I gave this talk in Scotland, I told them, well, this place is so remote that, the sun has set on the British Empire, but the news has not reached this town. So I thought that was kind of amusing when I saw this. This is the antenna, and you can, there will be two, but this is has two sort of hexagonal plates. So it's so-called dipole antenna. And then there's this ground plane that is apodized. And, this is supposed to minimize the effect of the ground rather than putting a ground plane on the actual ground itself. So that's a bit the idea. I don't think this is, kind of necessarily ideal. You would ideally have a much bigger structure that would be directed toward, away from the galactic plane where you have less synchrotron radiation, but with a limited budget, you sort of have to do the best that you can. Okay, this is if the calibration is a bit tricky, and I'm sometimes a bit surprised with, some of the stuff in the literature. So here there's a black, which is a noisy amplifier. So you don't really know what the noise is. And then the idea here is that you look at the sky. So that's going to have one temperature for a particular antenna pointing. Then you have a cold load where the temperature. So this is some sort of a resistor. And then you have a hot load, and you switch between the three, and you have the power out that you measure, and then there's the input signal, and there's also a noise that you don't know. That here there are two unknowns, and you have three temperatures. So by switching back and forth, it would seem that this would be a way to measure the sky temperature. So you could say this is sort of a black body, far away in temperature, and you're using the Jensen-Nyquist noise. So that this is basically what some variation of this is what everybody does. So if we analyze this, it really doesn't work that way, because if you take linear amplifier theory, you can represent an amplifier as a noiseless amplifier. And then there are two sources, that this is a voltage source and this is a current source. So these would be described by, random complex coefficients. And if you describe this distribution at a particular frequency, there's the RMS of the voltage, the RMS of the current, and noise. And then there are two real parameters that describe the correlation. So you have four real parameters. And then the problem is that the impedance of your sources and your antenna are not going to be the same. And so you don't have enough parameters with this setup. So you really need to do some careful modeling, and you also need to know what it's not a pure resistance, but you see it through some cable transmission line, which adds a reactive component, and then there are also parasitic reactive components. So the classic Johnson-Nyquist formula is a little bit too naive at the required accuracy, where you want to measure things to, ideally differences in the tens of microkelvin compared to, 5,000 Kelvin. So this is sort of the accuracy. So as you can see, if we compare reach with the competition, there are a lot more different sources here in these switches. And then there's a built-in vector network analyzer that, characterizes all of the electrical parameters. So this, allows for a calibration on site with a lot more redundancy. So I will just show, this is some work that Daniel Molnar and myself did, where we, came up with sort of general theory of noisy endports. So the two-port stuff is, very old. There's a classic paper from House on noisy amplifiers from, it's either 1960 or 1961. And then this is some work where we calculate the noise from the transmission line. So if you have a hot source, then you try to connect it to electronics at room temperature, and their losses, then you also get Nyquist-Johnson noise, and this allows you to calculate with a complete temperature profile. And there are four parameters that are required to model the properties of a noisy transmission line. So I don't know how relevant this will be, but we're looking at doing more accurate modeling for the calibration to make sure that that's done right. Okay, so I guess conclusions. Well, the first conclusion is that I think this is an experiment worth doing, because we will get new constraints on the first stars and the first quasars, and this is a part of astrophysics, where we really have very little data. Second point, this measurement is complementary to experiments such as Hera and also Hyrax, which, look at differences in the 21 centimeter between different directions and frequencies. So this is an absolute measurement, and it's easier in some respects. The signal is in millikelvin is bigger, but there's the absolute character of the measurement, which creates a lot of problems. So there are no good comparisons. You can't make an artificial galaxy. Modeling is going to be crucial to understand what you're measuring. And I didn't talk about antennas, but the antennas are achromatic. And so, you can get other artifacts from seeing more or less the hot part of the galaxy, and that's not going to follow the smooth spectrum that you expect from synchrotron radiation. So this is a hard experiment to do, and hopefully Reach and other people will make some progress in this area. And it would be nice if everyone sees a signal and agrees what it is in a number of years. So thank you for your attention.
Thanks, Prof. Martin. Thanks for the very good talk. Yeah, we have some time for questions. Any questions from the audience?
Thanks. Nice talk. The ground plane, was that by some kind of simulations that structure was designed, or it was just whatever was could be put in place?
Okay, I joined after it was designed, but yeah, I mean it was simulated. And maybe I'll also say a bit about the other antenna. So that's supposed to be a helical antenna, and that's interesting because it has a bit more directivity. Not a lot more. And also the polarization dependence is a bit different with the helical antenna. So helical antennas are, at least if you look at the center of the beam, they measure circular polarization. And we believe the amount of circular polarization in the sky is very small, so that gets rid of some other problems. But there's, I mean, if you look at this antenna, like the edges antenna, there's, quite a bit of sensitivity, what is near the horizon. One of the things underway with the antenna modeling is the chromaticity, and one of the design requirements is that there shouldn't be, whatever chromaticity there is should be easy to model and take out. So it's not a very sharply defined requirement, but that's one of the challenges.
Thanks, Martin.
Any other questions?
Can I ask a question?
Yeah.
Of you, what is what is the status of PRISM in Marian Island?
I think Prof. Kavi and Ma here can answer it better than me. Kavi?
Hi, sorry. Yeah. I think the data was taken until last year, but yeah, we kind of, well, I guess Cynthia and John decided that it wasn't. I mean, there were some incidents there, so it wasn't very safe to continue operations. So they have. So the equipment is now being packed up and brought back. I think. Uh, so yeah. So the observations won't continue, but the I think there is data in the can that they're analyzing.
So they're going to the Arctic, or I
Yeah, I think they're
about
planning on.
MIST, I think.
Sorry?
The MIST experiment.
Yes, yeah. So that's a kind of continuation of the effort on Marian Island.
So do you think you will have you know, with the data taken in Marian Island, that you have a good shot at giving a thumbs up or a thumbs down to edges? Or
Oh, Martin, to be honest, I haven't been really involved at all. So I mean, we should check with John or Cynthia.
okay, anybody available to share inside information? I mean, I'm curious.
Yeah, I'm not really sure. I don't know who most recently has been working on the data, but I can check with John and Cynthia and let you know.
Okay, thanks.
So I wonder for Saras, the Indian experiment, you said it gave a different result than AGES. But do they measure a curve of the brightness temperature? I mean, I don't recall to see such figures before. So not sure what base they claim to be against AGES result.
Well, they have a paper in Nature, I believe. And is this Yingxie?
Yeah, I'm Yijima. Yes.
Okay, I recognize your voice.
Oh, thank you.
If you like, I can send you the paper with our claims. And I mean, privately, you know, one of the criticisms of my colleagues of both EDGES and SARAS is that they're not making their data publicly available. And, you know, REACH is promising to do that. And, you know, I can appreciate some sort of reluctance to do that. But
Yeah, but even that is one aspect. But do they measure the brightness temperature? How deep is their curve?
I can't tell you right off. I mean, I know they are claiming that they can roll out the EDGES trough. But from what I remember, they're not
on what
claiming
base?
They're not claiming to have made a detection at another level, you know. So
do you mean their curve is consistent with zero? The error bar is large enough to make their curve to be consistent with zero?
I believe so.
I
mean,
just never
it's
see
more
such a plot.
daring. It's more daring to if you would, for example, take their template, which has some sort of strange things with the shape as well. you know, the flattening, you know, you get a lot more sigma for rolling out something at 500 millikelvin than, you know, making a detection. Yeah, I'm sorry, I'm really not.
Okay.
I know what's in their abstract, but I have not looked at the details.
No problem.
I mean, these papers are hard to read. So the Edges paper, I mean, this is a bit off the record, but you know, this is just my personal opinion. There is not enough information how they did the modeling for someone from the outside to easily to say, well, I believe this or I don't believe this. And you know,
I agree.
to do better.
Yeah, I agree. Yeah. I think we had such a talk on CNRS maybe more than 1 year ago, maybe 2 years ago, and that is also I just can't remember the details, but it's also quite perplexed. Yeah.
So you came away skeptical. Any other questions?
Yeah, I don't see any other questions, and we are close to the time. Thanks. Let's thank Prof. Martin again. Thanks for joining and giving a wonderful talk. And thanks everyone for joining today.